Now we get to a topic that I know you've been anxious to get to for a long time. I've been promising you the derivative of the exponential function for a long time, and now it's time to do it. But before we do, we'd better look at the definition of e, which is the base of your exponential function, of your most natural exponential function. E is defined in one of two ways. We can define it as the limit as h goes to infinity of 1 plus 1 over h to the h, and that equals approximately 2.718281828. Don't get the idea that this 1828 keeps repeating itself. This is an irrational number and there's no pattern to it. And this is just a coincidence that these digits happen to repeat themselves. They don't repeat again in the next place. Although eventually, since this goes on infinitely, they'll almost certainly repeat again. Okay, an alternative definition is the limit as h goes to 0 of 1 plus h to the 1 over h. There's no difference in these two definitions. For example, h goes to infinity. Let h equal 1,000. You're going to have 1 plus 1 1,000th, which is 1.001 raised to the 1,000th, right? Now, h goes to 0 here. Well, let's let h equal 0.001. Then we have 1 plus 0.001, which is 1.001, the same as it was up here, to the 1 over 0.001. Well, 1 over 0.001 is 1,000. So we have 1.001 to the 1,000th power if we let h equal 0.001 here, and the same thing if we let h equal 1,000 here. There's really no difference between these. And you can put larger and larger h's into your calculator, and you'll get closer and closer to this number. Or smaller and smaller h's into this expression, and you'll still get closer and closer to this number. Now, your text doesn't discuss the only approximation you really need in order to derive the expression for the derivative of e to the x. And I'm going to show you a little bit about that because I don't think it's that esoteric and I don't think it's that far out of the way, and I think it's kind of important that you know this. So what's e to the x? Well, e is the limit of, let's use this expression. E to the x would be then this expression raised to the x power. And then we'd have something like a power, we've got a power 1 over h to the power x. Now, again, get a little bit uncomfortable. This x is outside this limit. If we put parentheses around this limit, we raise the whole limit to the x power. How does the x go inside of the limit operator? So that we have x times 1 over h. Can we do that? Again, take my word for it, you can, but you'll be anxious to see a proof of this sometime before too long. Okay? So this is something else that you can do with limits, but we haven't proved it. So again, you should be a little uncomfortable. You don't know why this works, but it does. Now, of course, the exponent here becomes x over h. If we let k equal x over h, then we can replace this exponent here by k. And in fact, h, if we solve this for h, we just multiply both sides by h and divide by k, we get h equals x over k. So we could replace x by h by x over k. Now, using the binomial theorem, it's not too difficult to show that for small values of x, this quantity here, this limit, is approximately 1 plus x. And there's some details about that in the notes that you're working from, in the class notes that have been posted and distributed on CD. So you can look at a few more details of that, but it follows from this rearrangement that we can say that this limit is about 1 plus x if x is small.